Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is the second half of a lecture on completing the square. The first half, we actually introduced the idea of what completing the square really means. It's a very important video actually to watch to make the idea of completing the square a little more whole for you. In this part, we're going to use completing the square to solve quadratic equations. However, I have to let you know that honestly, it's not one of the best techniques that I would that can be used to solve quadratic equations. A lot of instructors tend to really love forcing students to go through completing the square to solve a quadratic equation, but honestly, like I said, there are better methods. Let's go ahead and recall what completing the square is. Given a polynomial, x squared plus bx, we would add 1/2 of that b term squared to make it a perfect square. Now let's see how we can use that to actually solve an equation involving a statement that has this term, an x squared plus some number times x. And then we're going to expand that into solving general equations that involve 3x squared plus 5x or something like that. Suppose somebody gives you a quadratic equation like the following, x squared plus 6x plus 5, and they ask you to solve this. Now, before you jump into some fancy techniques for solving a quadratic equation like this, you should think to yourself a few things. One, ask yourself how many versions of your variable there are. In this case, there are two. There's a squared version, and then there's a regular version of your variable, which means you're going to have to rely on special techniques. The second thing you should try really is to try to factor this. If factoring works, then that's the best way to go. And actually, this does factor to x plus 5 times x plus 1. So that quadratic expression on the left-hand side factors to this. And of course, this is supposed to equal 0. And in this case, we can use the zero factor property to say, well, if the first object times the second object is equal to 0, like this, we have two objects that multiply to become 0, then either the first one has to be 0 or the second one has to be 0. So we've had some experience with this, or you should have up to this point. So I'll show you that this is true, and now you can subtract 5 from both sides in the first equation to get x is equal to a -5, or subtract 1 from both sides in the second equation and get x equals to -1. That's how I would highly recommend solving this quadratic equation. But let me show you another method using the ideas that we've introduced in the last lecture. We have x squared plus 6x, and I'm going to put a big old space there and say plus 5 is equal to 0. The reason why I have that big old space there is because I'm going to actually add something in here in a moment. Before I do, I'm going to show you, I'm going to go ahead and subtract 5 from both sides. In other words, I'm just going to get all my stuff with variables on the left-hand side, or A side, and get everything without a variable to the other side. All my constant terms are on the right-hand side, all my variable terms are on the left-hand side. And now what I'm going to do is complete the square on the left-hand side. So like I said, first thing I'm going to isolate the variable terms. And the second thing I'm going to do is complete the square. And when I say complete the square, I mean really complete the square on the side that happens to have your variable terms. So remember, to complete the square, you add half of this number, so half of that 6 is going to be 3, squared. Of course, we started with an equation, and an equation says that one side is equal to the other side. Well, if I just add 3 squared to the left side, I'm changing this equation. So to keep it the same, I'll have to add that 3 squared to the right-hand side as well. Notice that in this case, nothing about this statement has changed. It's like, remember, equations are like teeter-totters, and we've just added 9 pounds of weights to the left-hand side. You better add the same number to the right-hand side to keep this balanced. Let's go ahead and now show what completing the square allows us to do. Remember, this will factor. I'll steal this x, and I'll steal that positive 3 squared. If you don't believe me, you can take a look at that trinomial. It's x squared plus 6x plus 9 and try to factor that. It's going to be x plus 3 times x plus 3. The right-hand side is negative 5 plus 9, or in other words, it's going to be 4. So I'm just going to actually write it as 4 instead of that business. And now we're actually in a very simple equation here. How many versions of my variable do I have at this point? The answer is 1. I just have one version of my variable. It's that one right there. And so now I can undo the stuff that's happening to it. In other words, I could take the square root of both sides. And remember, when you take the square root of both sides of an equation, you get plus or minus. The square root of 4 is just 2. And then I'll subtract 3 from both sides. So this implies x is equal to, and I could write plus or minus 2 minus 3, but I like to write that subtraction of 3 up front. Just a habit I have. So here's the deal. I have two answers. I either have x is equal to a negative 3 plus 2, or x is equal to a negative 3 minus 2. When you do the math there, it's x is equal to negative 1 or x is equal to a negative 5. And if you look at our original answers way back when, that's what they were as well. This is solving by completing the square. And like I said, it's not the best method to use. It works great if you cannot factor a quadratic. It works very well for that. But if you can factor, always try to factor first. So let's try this one, x squared minus 3x minus 6. When you take a look at that, that actually cannot factor. So now we are pretty much stuck using special techniques beyond factoring. I see I have two versions of my variable, so I'm going to require some special technique to solve this. I've tried factoring, or I've thought about factoring, but it's not going to work here. So the next thing I'm going to try is another special technique, and that would be, in this case, completing the square. Let's go ahead and isolate all the variable terms on one side. So I'll add 6 to both sides, essentially, is what I'm saying. And then I'll try to complete the square on the terms on the left-hand side, basically to create a perfect square trinomial on the left-hand side. So I'm going to go ahead and add some object squared to that side. And of course, if I add some object squared to one side, I have to add it to the other side. That object is going to be half of this middle term. Half of that negative 3. And I love writing it like that because it really does help me out in the next step. Remember, the next step, I would normally say, oh, that's x squared minus 3x plus 9/4, and try to factor that, but that's a pain to factor. It's much better just to note it's going to factor to where I borrow one of these x's and I borrow that negative 3/2. That's how it's going to factor. Remember, there's a square here. On the right hand side, I'm going to have to actually do a little bit of math over here. 9/4. 6, as far as having a denominator of 4, is the same thing as saying 24/4. So this tells me that I have x minus 3/2 being squared is equal to 24 plus 9 is 33/4. At this time, I'll go ahead and notice that I only have one version of my variable here instead of the two versions, the square and the regular. Now I just have a regular old x. So I can start solving for that by taking the square root of both sides first. On the left-hand side, that would leave me with x minus 3/2. On the right-hand side, I'd have plus or minus the square root of that business there. And there is a little extra work I can do on that right-hand side, honestly. Remember, and maybe you don't remember this, but I'll just tell you right now, if you have the square root of a fraction, It's the same thing as saying square root of the numerator over the square root of the denominator, as long as that denominator is not 0. So I'm going to rewrite this fraction here as the square root, so let me do plus or minus the square root of 33 over the square root of 4, which happens to be 2. And now I will go ahead and add that 3 halves to both sides. Remember, right, because we're subtracting 3 halves, we have to do the opposite of subtraction, which is addition. So I'll have a positive 3 halves, and then plus or minus square root of 33 over 2. That's a great answer. It looks good to me. I just want to note this is perfectly fine, but it's also interesting to see that this can be written as 3 plus or minus the square root of 33 all over 2. And if you've ever seen the quadratic formula has that look to it. Has a number plus or minus the square root of some other number divided by some number. That's just something interesting to note. From this point forward, it'll just be practice using completing the square, but there is a little extra nudge I have to give here. If you remember, if you can factor it, try this. I'm going to see if I can factor as 2x times x. Let's see, two numbers that multiply to a negative 2 would be like a 2 and a 1 maybe. Let's see if I can do this. That's positive, that's negative. If you multiply those two things together, you get positive 4x minus 1x, that's a 3x. Negative 1 times 2 is negative 2. Yeah, this is actually how it factors. So there's no use or no reason for me to use completing the square on this. My answers will actually be x equals 1/2 or x equals a negative 2. See how quick that is when you try to factor? It's very nice. Just to let you know, and I will do another example involving this, we can do this using completing the square, but there's something that you have to remember about completing the square. The form for it requires that the coefficient on x squared is 1. Not 2, not negative 2, not 1.1, but 1. In our case here, we don't have a 1 in front of our x squared. It's still not such a bad thing. You could start doing this if you know that factoring doesn't work, which it actually does in this case, but if you want to do this using completing the square, the first thing you would do is force, so I'm kind of adding on parts to our method, force the coefficient of x squared to be 1. And then follow the rest of the steps, which is isolate the variable terms, complete the square, and then solve. So let's do that here. Let's force this variable, the coefficient of x squared to be 1 by dividing each of these terms by 2. So if you divide each of these terms, I'll show you this right here. I'll divide both sides by 2, which means dividing every term in this equation by 2. You get the following: x squared plus 3 halves x minus 1 is equal to 0 over 2 is still 0. Now I'll go ahead and isolate the variable terms by adding 1 to both sides. And I will complete the square by adding some object squared to both sides. Remember, you're adding an object squared. And that object is half of that 3 halves, which is a positive 3/4 actually. That's half of 3 halves. So you're multiplying the denominator by 2. That's the same thing as dividing by 2 is multiplying denominators by 2. And of course, having done this a few times, I know this is going to factor, steal that x, steal that positive 3/4. Remember, it becomes a square. So it becomes an x plus 3/4 quantity squared is equal to 1 plus 9/16. And this is going to be 16 over 16 plus 9/16, or in other words, 25/16. So let me rewrite that. And now I'll take the square root of both sides. So I'll get x plus 3/4 is equal to, remember taking the square root of both sides means that you get plus or minus. Square root of 25 is 5, square root of 16 is 4. And now I'll subtract 3/4 from both sides. And again, remember, subtracting 3/4 from both sides means essentially you can either write the subtraction of 3/4 at the end of it, or you can say a negative 3/4 at the beginning of it. They mean the same thing. And that's our final answer. Is it improper to leave it like this? No. But some instructors, not myself, but some other instructors might want you to combine numerators since their denominators are the same and say this is the same thing as saying negative 3 plus or minus 5 all being divided by 4. And if you really want to break this down, that means that x is equal to a negative 3 plus 5, which is 2 over 4, or x is equal to a negative 3 minus 5, which is a negative 8 over 4, which means that x is equal to 1/2, or x is equal to a negative 2. But again, lesson learned, if I can factor, much faster, right? This one's already in an odd form because the fact is that we have two different versions of our variables, of our variable actually, but they need to be on one side. So I'm going to first rewrite this as being a 5x squared and add 17x to both sides. So I get a plus 17x minus 40 is equal to 0. Again, I'll ask if this factors. It might actually. If it did, it'd be a 5x and an x. And two numbers that multiply to 40 would be like 1 and 40, but I'm not going to write those two down. 2 and 20, or 20 and, or the other way around. 2, 3, 4 and 10, or 4 and 10. 5 and 8. 5 and 8. And so you can go through here and check, like 5 times 20 is 100. That's just 2, so 100 and 100 and then 2 cannot be combined to get you to positive 17. So that one is definitely out of the running. 5 times 2 is 10, and then you have a 20. A 10 and a 20 cannot be combined in any form or fashion to get you to a 17. 5 times 4 is 20, and then we have a 10. Well, those can't be combined to get to 17. 5 times 10 is 50. 4 times that 1 is 4. 50 and 4 cannot be combined to get to that 17. 5 times 5 is 25. 8 times 1 is 8. So 25 and 8 actually can be combined to become 17. Let's see, negative 5. No, it'd be a positive 5 and a negative 8. Let's see. Check the math here. 5x times x would be 5x squared. 5x times 5 would be 25x, minus 8x would be a 17x actually, and then negative 8 times 5 is a negative 40. So we know our answers are going to be x equals 8/5, or x is equal to a negative 5. And I would be done. I would not want to complete the square on this. However, let's practice completing the square because, well, that's important. So to complete the square, remember the first thing that I would do is divide each term by 5. So I get x squared plus 17/5 times x minus 8 is equal to 0. Remember, I divided every term here, including the terms on the right-hand side, which there's only one, by 5. Now I'll isolate the variable terms. So I have x squared plus 17/5 x is equal to a positive 8. I should put my implication signs in here. Sorry about that. And at this point, we're going to start completing the square. I'm going to add some number squared to each side. And that number will be half of this 17/5. That'll be a 17/10, actually. So here we go. I know that the left-hand side will factor to x, and that's a positive 17/10 quantity squared. The right-hand side, That's going to be 8 plus 17 times 17 is 289. 10 times 10 is 100. Well, okay, that 8 can be written with 100 in the denominator by multiplying top and bottom by 100. So I'll have 800 over 100. And add them up. And get x plus 17 tenths being squared is equal to 1089 over 100. And I'm going to take the square root of both sides. Now when you go to do this, you should probably check to see if you can take the square root of 1089. So that's not one that people have memorized, so it's just good to check. By the way, if you're using a graphing calculator, all I did was hit the second button to access the yellow parts of the keyboard, and hit the key corresponding to the square root, and typed in 1089. And that actually we do happen to have the square root of. Square root of 1089 is a positive 33. Let me go ahead and close this out. All right. So this, when I take the square root of both sides, I'll get x plus a 17 tenths is equal to plus or minus. Now remember that plus or minus is so important because so many people forget it. Plus or minus 33 over 10, because the square root of the numerator is 33, the square root of 100 is 10. And now I will subtract 17 tenths from both sides to get the following. X is equal to a negative 17 over 10 plus or minus 33 over 10. So our solution should be a negative 17 plus 33, which is going to be what, 13, 14, 15, 16 over 10, which can be reduced down. They're both divisible by 2, so that reduces down to 8/5. Or x is equal to a negative 17 minus 33, and that's going to be a negative 50 over 10. Negative 50 over 10 is a negative 5, which again matches our original set of solutions in the McDonald's colors. So let's try our hand at something a little bit more challenging. Since this should be a college level algebra course, let's solve this quadratic equation, which has a strange looking variable on the front end. It's actually not a variable, that's what we call a parameter. Most people call it a constant, but honestly it's technically called a parameter. But we're going to solve this quadratic equation by completing the square, because I can't factor this because I don't know what a is. To do this, you just still follow the same steps. Remember, you want that coefficient to be 1, so get, in a shorthand notation, I'll just say get 1x squared. And then second thing to do is isolate x's. I'll say variable terms. It's probably more technically correct, I guess. Isolate variable terms, and then complete the square. Complete CTS, complete the square, and solve. So we're going to try to do that here. The first thing we need to do is get a 1 in front of that x squared instead of an a. The best way to do that is to divide each side by a. And when I say divide each side, it really means divide each term by a. Of course, there is something to be said here. We're assuming that a is non-zero. We are assuming that a is a non-zero number, which is, I think, a pretty safe assumption. On the first term, a over a is 1, so we get a regular old x squared. We'll have a negative 2 over a times x, and then positive 6 over a is equal to 0 over a, which is just 0. Now I'll go ahead and keep all the variable terms on the left-hand side and move all the constant terms to the right-hand side. And remember, a is considered to be a constant term here. So we'll go ahead and subtract 6 over a from both sides. So I'll have x squared minus 2 over a x is equal to a negative 6 over a. And at this point, we're going to start completing the square. So we're going to add some number squared to both sides. So notice that nothing's changed between what we were doing all the way up to this point in this lecture and what we're doing now. This is completely the same stuff. We're going to add half of this negative 2 over a business. So 1/2 of that negative 2 over a to both sides. So 1/2, and actually technically it's 1/2 of that negative 2 over a squared to both sides. So let's clean up inside the parentheses first just to see what that looks like before I start factoring. X squared minus 2 over a times x plus the 2 goes in that 2 once, so I get this. It's a negative 1 over a being squared is equal to a negative 6 over a plus a negative 1 over a being squared. And I know that people, when they watch my lectures or they attend my lectures in a course, they often ask me why I keep that negative in there, and I've already said it a few times in this lecture. I keep it in there because it allows me to remember how this is going to factor. I'm going to steal one of these x's and one of these pictures in here, which is a negative 1 over a, and that's super important. And finally squared. The right-hand side of this negative 6 over a plus negative 1 squared is just a 1, and a squared is an a squared. Now, there's not much that I can do except combine these two fractions, but in order to combine those two fractions, they have to have the same denominator. So I'm focusing on the right-hand side here, and to get them to have the same denominator, I'll need this first fraction to have a squared in its denominator. So I'll multiply the bottom by a, but remember, you multiply the bottom of a fraction by a, and you're trying to add two fractions, you better multiply the top of that fraction by a as well. So this is going to be a negative 6a over a squared. So when I add those two fractions up, I get this beautiful result. X minus 1 over a being squared is equal to a negative 6a plus 1 all over a squared. And now I'll take the square root of both sides. And remember, when you take the square root of both sides to unlock a square, you're going to have a plus or minus. So this becomes an x minus 1 over a is equal to the plus or minus of the square root of the right-hand side. And if you don't mind, I'm going to write it like this. Instead of negative 6a plus 1, I'm going to write it as 1 minus 6a. It doesn't really make much of a difference. It's just a habit that I have. Now, I'm going to do something here that any mathematician would probably yell at me if I don't describe it. So for the moment, I'm going to wave my hands and say, well, let's break this square root into the square root of the numerator over the square root of the denominator. That's still not what people would yell at me about. They would yell at me about this. What's the square root of a squared? Well, square roots undo squares, so that would be an a. So I should have a plus or minus square root of the numerator all over just a regular old a. Now I'm going to fix something a little bit later, but for now, I want to leave it like that and not explain something. I'll explain something in a moment, though. We're almost done solving. All I have to do is add 1 over a to both sides. Before I do, I'm going to go ahead and erase what I have up above and create a little more room down below by roping this up and just carrying it on up here. Just makes my life a little bit easier. All right. So let me add 1 over a to both sides, and I'll get this. X is equal to a positive 1 over a plus or minus the square root of that numerator over a. And notice these both have the same denominator. So I have a fraction with a as a denominator plus or minus another fraction with a as a denominator. So you could write that actually as a single fraction. 1 plus or minus the square root of 1 minus 6a, all being divided by a. And that is the final answer. That's as good as it gets. So let me highlight that and call it a day on that one. And then kind of explain to you what I was worried about somebody might email me or yell at me about. At least if I don't describe it. So there is a little subtle note here. And you can rewind the lecture to see this. But we had a moment here where we had, I think it was 1 minus 6a over a squared all underneath the square root. And we broke this out. And by the way, it was a plus or minus. That's the important part here, actually. We broke this out as a plus or minus 1 minus 6a underneath the root all over the square root of a squared. Technically speaking, the square root of a squared is not equal to a. It's equal to the absolute value of a. If you don't believe me, just ask yourself, what's the square root of a 3 being squared? This is not a trick question. What's the square root of 3 being squared? Well, 3 squared is, okay, and the square root of that is 3. So 3 squared is 9, the square root of 9 is 3. Okay, well, it looks to me as though the square root undoes the square and gives me that 3 back. But watch what happens here. All right. Negative 3 being squared is, and the square root of that is 3. Negative 3 being squared is 9. In other words, once I squared that negative, all reference to a negative number inside that square root disappeared. So I squared a negative 3, became a negative 3 times a negative 3, which is a positive 9. And we all know the square root of a positive 9 is a positive 3. So here is where I'm telling you, saying the square root of some number squared returns that number is not true, because the square root of a negative 3 being squared didn't return a negative 3. It returned a positive 3. So in general, we say it returns the absolute value of a. In other words, the positive version of a. Of course, there's something subtle going on here. Knowing what the absolute value is, since we're in college level algebra, we can talk about this. The absolute value of a is just a, really, if a is positive. In other words, if a is 10, well, the absolute value of a is just 10. If a is a negative 10, though, then it's the opposite of a. So in other words, if a is a negative 10, it's opposite of negative 10, which is a positive 10. So this absolute value business, if I were to have used it, I'd have this, plus or minus the square root of 1 minus 6a all over, technically, the absolute value of a. And then we take this in cases and say, well, is a positive? Then this would be positive. Is a negative? Then it would be negative. In other words, this could be plus or minus a, right? It could be plus or minus. We don't know. It could be positive or negative. Guess what this says? The same thing I just said. It could be positive or negative. So that statement right there is why I don't have to actually write the absolute values, because that's taken into account that, well, that a could have been negative, it could have been positive, so we'll just write in plus or minus. We don't know. If you didn't follow all of that, that's totally fine. It's just something I wanted to include for those who are sticklers for rigor. It is true. Now, as a final example, I want to talk about this style of problem. Solve v equals pi times the quantity r squared plus r squared times h for capital R. Whenever you're asked to solve a formula for a variable, I personally have always found it to be a good idea to think about what's happening to your variable. If you only have one version of your variable, which we are lucky enough to only have one version of capital R here. Yes, I know we have a lowercase r, but that's a totally different variable. If you only have one version of your variable, then write out what's happening to it. The first thing that somebody did to that capital R is they squared it. After they squared it, they had r squared. And what did they do to that? Well, following the order of operations, inside this parenthesis, they added a little r squared to it. But after they added that little r squared to it, what was the next thing they did? Now we have a little r squared plus big R squared. What happens to that? It turns out they multiplied that by both a pi and an h. Right? They grouped up this pi and this h and multiplied against that picture, that middle picture. That's how they hid the value of capital R from us. So that's what we're going to do. And again, if you haven't watched all my lecture series, I call this tying the knot. That's what they did to tie up the variable. The whole idea of somebody hiding the value of r from you is that they surrounded it with a bunch of operations like squaring, addition, multiplication, subtraction, division, anything like that. And how you untie a knot is you start with the last thing that they did. The last thing they did is they multiplied by pi h. So you have to untie that. The opposite of multiplication is division by pi and h. And then the next thing you need to untie, climb this ladder here, they had added r squared. So we're going to do the opposite of that. We're going to subtract r squared. Finally, the first thing they did was they squared. We are going to take the square root. That's the opposite of squaring something. So let's follow these operations here. If I divide both sides by pi h, you'll see on the left-hand side nothing cancels. We just have a v over pi h. But on the right-hand side, pi over pi, those common factors cancel, and h over h, those common factors cancel, and I'm left with a little r squared plus a big R squared. Now, following what I told myself I'm supposed to do, I'm going to subtract little r squared from both sides. So subtract it from the right, subtract it from the left, and remember that little r squared is not a common or not a like term with the other variable term there, so we just have this v over pi h minus little r squared is equal to a big R squared. And now I see the last thing I need to do is take the square root of both sides. Just remember, when you take the square root of both sides, it becomes a plus or minus the square root. V over pi h minus little r squared. And that's it. You're done. That's been solved for capital R. Good tactic to use whenever you're solving a formula for a variable. I know this seems kind of out of place in this lecture, but it's always good to kind of review solving formulas for variables anyway. So it's good to sneak one in every now and again.